So moving on to differential equations that can't easily be solved using the integrating factor, another type is the exact differential equation. And the exact differential equation is written of the form some function of x and y times the differential of x plus some function of x and y times the differential of y is equal to 0. And I know definitely that when I was first looking at this equation, I thought to myself, well, what does this even mean? Times the differential of x times the differential of y? How do I solve this? So the way that we solve this is, well, first let's divide everything by dx to make this seem a little bit more familiar. So I'll make some function of x and y plus another function of x and y dy dx equals 0. And so we define our function, the function that is the solution to the differential equation f. So we say f sub x, the partial derivative of f with respect to x, has to equal to m. And we say our partial derivative of f with respect to y is equal to n. And so if I write this more clearly, so you'll see more of the intuition behind how we solve this, you'll see df dx is equal to m, and df dy is equal to n. So now let's think to ourselves, well, how will we be able to relate m and n? Well, we know that d2f over dx dy has to equal to d2f over dy dx, because that's how we define our second partial derivatives. So by that logic, we'll know that dm dy has to equal to dn dx. And if this solution is not satisfied, then this is not an exact differential equation. And so let's go through an example with this. So an example of this is seen by the differential equation y cubed dx plus 3xy squared dy is equal to 0. And so let's see, our m is going to be y cubed, or we'll see if our m is y cubed. We still have to determine whether or not the solution is exact, or the equation is exact. And our n, it's supposed to be an n, is 3xy squared. And so let's see, what's dn dx? dn dx is equal to 3y squared. And that's supposed to equal to our dm dy. And our dm dy, m is y cubed, sorry about that. So then dm dy is 3y squared. dm dy is 3y squared. So it fits the conditions for exactness. So we can carry on with solving this. So if the partial derivative of f with respect to x is equal to m, f sub x is equal to m, which is equal to y cubed, then if we integrate everything with respect to x partially, then we'll get f is equal to y cubed x. And you might think there's going to be a plus a constant, but remember, this is the partial derivative with respect to x. So if we're integrating with respect to x, then we're going to get an entire function of y. Because remember, if we take the partial derivative of this with respect to x, this entire function of y will equal to 0, and we'll get y cubed again. Now, we'll take the partial derivative of this with respect to y, and we'll set this equal to n. So then, 3y squared x plus f prime of y is equal to 3xy squared. And so we can cross both of these out. That means f prime of y equals to 0, and thus f of y is equal to c, because again, since we've already eliminated the extra function term of the y, we'll know that f of y is just going to be the constant. So plugging this all back in, we'll find that the solution to the differential equation is f is equal to, and I'll just rearrange the constant because it looks cleaner this way, c is equal to xy cubed.